In this lesson, we're going to explore alkene addition reactions, and along the way, see how reaction mechanisms can help to predict reaction outcomes. The main mode of reactivity for alkenes is through electrophilic addition. Electrophilic addition is an addition reaction of an electrophile across a carbon-carbon pi bond. So here's an example of an electrophilic addition. We have an alkene, which will serve as the nucleophile, reacting with an electrophile. Here, XY is the electrophile. And you can see that the XY molecule literally added across that pi bond. One thing that needs to be considered when looking at an electrophilic addition reaction is the regiochemistry of the reaction. Some electrophilic addition reactions are regioselective. A reaction is regioselective when some product constitutional isomers are preferred over others. In this context, the different product isomers are referred to as regioisomers. For alkene addition reactions, regioselectivity is really only a concern when the alkene is asymmetrically substituted. That is, when it has different substituents on each carbon of the double bond. So here I have an example of a differentially asymmetrically substituted alkene. You can see that on one carbon of the double bond, there are two methyl substituents, and on the other, a methyl and a hydrogen substituent. When this alkene undergoes an addition reaction, two possible constitutional isomers can form, and that's based on which side of the alkene each part of that electrophile ends up attached to. So in the first product, you can see that the X of the electrophile ended up on the left side of the alkene, and the Y ended up on the right side. But in the second product, you can see that the Y ended up on the left side of the alkene, and the X on the right. So if an alkene addition prefers to form one of those products over the other, it's considered regioselective. So we're going to look at three specific types of electrophilic additions. The first is hydrohalogenation, which is just the addition of a molecule of one of the halogen acids, HF, HCl, HBr, or HI. So in this example, you can see that I have an asymmetrically substituted alkene. On the left carbon of the double bond, we have two methyl substituents, and on the right, two hydrogens. And that means that this reaction could form two regioisomer products. You can see that the first product has the bromine attached to the leftmost carbon of what used to be the alkene, and the hydrogen is attached to the right carbon. And in the second product, you can see it's reversed. The hydrogen atom is attached to what used to be the left carbon of the alkene, and the bromine is attached to the right. And when hydrohalogenation is performed on an asymmetrically substituted alkene, it is regioselective. The reaction favors placement of the halogen onto the more highly substituted alkene carbon, giving rise to the more highly substituted alkyl halide product. Let's take a look at the reaction mechanism. Remember, anytime you're dealing with learning a new reaction mechanism, if it's a polar reaction, the first thing you really want to do is to identify the roles of the nucleophile and the electrophile. So, in hydrohalogenation, the alkene is going to serve as a nucleophile. Remember that carbon-carbon pi bonds are nucleophilic. And that means that the HBr is going to serve as the electrophile. And if you look, there's a dipole on the HBr molecule that makes the hydrogen atom electron deficient. So electrons will flow from the electron-rich nucleophile, that is the carbon-carbon pi bond, towards the electron-deficient electrophile, and that's the hydrogen atom of the HBr. Now remember that in a reaction mechanism, when a nucleophile attacks an electrophile, it doesn't just give away its electrons. What's happening here is that carbon-carbon pi bond, it starts off shared between those two carbons. The electrons will move from being shared between the two carbons and in the end be shared between one of those carbons and the hydrogen that's being attacked. And of course, hydrogen can only have one bond because it only has one valence orbital. And that means that it has to push electrons off at the same time. So we have to break the HBr bond, depositing a lone pair onto that bromine. Now there is an ambiguity in this mechanism. Which side of the actual pi bond do the original pi electrons remain attached to? I like to think of alkenes as being a door that's hinged on both sides. If that alkene were to open up, if the door were to open and be hinged on the right carbon, that means that the electrons will now be shared between the right carbon of that alkene and the hydrogen. And that's what we see on this top mechanistic path. We see a new CH bond forming on that rightmost carbon, and when the electrons move away from the left carbon, it creates an electron deficiency. It makes a carbocation. It's also possible for the door to be hinged on the other side. If the pi electrons were to open up so that the electrons remained attached to the left carbon, you would now end up with a CH bond on that left carbon, creating an electron deficiency on the right carbon, making a new carbocation. And that's what we see on the lower mechanistic path. Whichever carbocation is formed, being a carbocation, it's rather unstable. It has an incomplete outer shell. And what we've done here is we've created a new pair of nucleophiles and electrophiles. The bromide will serve as a powerful nucleophile and attack the carbocation to create a carbon-bromine bond in a second step. So you can see that the product that forms is actually dependent on which carbocation forms, the tertiary carbocation or the primary carbocation. Regardless, it's a pretty straightforward, simple two-step mechanism. And again, the reaction prefers to place that halogen on the more substituted carbon of the double bond, placing the H on the less substituted carbon. That regioselectivity can be summarized by Markovnikov's rule. Markovnikov's rule states that any electrophilic addition of an HX-type molecule that proceeds through a carbocation intermediate will favor placement of that X onto the more substituted carbon of the pi bond. So here I have that exact same reaction drawn out now using skeletal structures. And you can see that the halogen ended up on the more highly substituted left carbon of that alkene. Using Markovnikov's rule, we can predict the outcomes of other hydrohalogenations. Here we have 1-butene. Reacting it with HCl is going to form this product here as the major product. Again, 2 regioisomers could have been produced here. One where the chlorine was placed on the left carbon, the less substituted carbon of the alkene, and one where the chlorine was placed on the right and more substituted carbon of the alkene. But Markovnikov's rule tells us that the preferred product will have the halogen attached to the more highly substituted carbon of the alkene. Keep in mind that Markovnikov's rule doesn't always apply. In the cases in which an alkene reacts that has equal but not identical substitution on each carbon of the double bond, you'll actually get a mixture of products. Take a look at this example. If you look closely at that alkene, you can see that the 2 carbons are actually equally substituted. Ignoring the double bond, each carbon of the alkene has 1 alkyl group attached to it. The carbon on the left has a propyl group attached, and the carbon on the right a methyl group. So the 2 carbons of that alkene are equally substituted, each having 1 alkyl group attached, but they are not identically substituted because the 2 alkyl groups aren't the same. Now, because both sides of that alkene are equally substituted, that means that Markovnikov's rule doesn't really help here, and you're going to end up with a mixture of products where the bromine attaches to either of those 2 carbons, in this case giving rise to 2 different secondary alkyl halides. So reactions like hydrohalogenation that obey Markovnikov's rule are called Markovnikov regioselective reactions. But why does hydrohalogenation exhibit this form of regioselectivity? Just about any aspect of a reaction can be explained if we look at the reaction mechanism and the energy changes that occurred during the reaction. Let's first analyze hydrohalogenation thermodynamically. Here we have a free energy diagram of that same hydrohalogenation using 2-methylpropene and HBr. Now remember, thermodynamics is the study of reaction equilibria, and it's tied to the energies of the reactants and the products. And that technically means that the mechanism is really irrelevant when looking at thermodynamics. Remember that the more exergonic a reaction is, the more product it will form. And in this case, we have the potential to make 2 products from the exact same reactants. And as you can see here, the 2 products actually have roughly the same energy. And of course, since both products are being made from the same reactants, that means that the reactants in each case have the same energy. So if the 2 different products have the same energy, and the reactants are the same to make either one, that means that just as much energy is being released in forming the green product, the major product, as is the red product, the minor product. And that means that at equilibrium, the same amount of each product will form. Well, that just means that the reaction is not under thermodynamic control. A thermodynamic analysis doesn't explain why the green product is the major product. And that means that it's not under thermodynamic control, it must be under kinetic control. And that means we have to look at the kinetics of the reaction. Remember that kinetics is a study of reaction rates. And if we do a kinetic analysis of this reaction, we need to know the mechanism, which we do. We know the reaction is a 2-step process that goes through a carbocation intermediate. In this case, because the reaction can form two products, it goes through two different carbocation intermediates. And if you look at the free energy diagram, you can see that unlike the products, those two carbocations that lead to the final products actually do have different energies. The tertiary carbocation that leads to the major product is actually more stable, it's lower in energy, than the carbocation that leads to the minor product. And that's because there's a stability trend with carbocations. The more highly substituted a carbocation is, the more stable it is. And that means that a tertiary carbocation is the most stable, then secondary, then primary, and then methyl carbocations are extremely unstable. Because that tertiary carbocation is more stable than the primary carbocation, the tertiary cation will form more quickly. And because the tertiary carbocation is formed more quickly than the primary carbocation, it means that the green product will form more quickly than the red product. And because the green product is formed more quickly, there'll be more of it produced. You could compare this to workers in a factory. Let's say we had a doll factory, and we had two workers, and both of them had the job of making dolls from a big pile of doll parts. Doll bodies, doll heads, arms, and legs. So let's say the pile had enough doll parts to make 100 dolls. And one of the workers worked very quickly, and the other worker worked very slowly. The fast worker is going to create a very large pile of completed dolls much quicker than the slow worker will. And when all of the doll parts are used up, that's it. The slow worker can't work overtime. There's nothing he can do to make more dolls if all the doll parts are used up. So the worker that worked more quickly will have the bigger pile of finished dolls at the end of the day. Because a kinetic analysis of this reaction explains the outcome, it's considered under kinetic control. So in our kinetic analysis of the hydrohalogenation, we actually cheated a little bit. Remember that reaction rate is actually determined by the energy of activation for a reaction, and that's the energy difference between the reactants and the transition state. In our kinetic analysis, we were actually looking at the intermediates and their stabilities and not the transition state stabilities. So how do we know that the two transition states leading to those carbocations show a similar difference in energy? Because it's really the difference in transition state energies that we need to look at, not the difference in intermediate stabilities. The problem is that transition states are transient. Their energies can't be directly measured, and they can't even really be drawn properly because they involve partially formed and partially broken bonds. So how can we compare the relative energies of transition states when we don't even know exactly what they look like? Well, the way we get around this problem is to invoke Hammond's postulate. Hammond's postulate states that in any reaction step, the transition state will more closely resemble the species it is closer to in energy, that is, the reactant or the product. So here I have a couple of free energy diagrams, one depicting an exergonic reaction and one depicting an endergonic reaction. If you look at the exergonic reaction, you can see that the transition state is closer in energy to the reactants than it is to the products. There is a smaller vertical distance between that high transition state and the reactants than between the transition state and the products. And because the transition state in an exergonic reaction is closer in energy to the reactants, it means that structurally it will actually more closely resemble the reactants than the products. If you look at the endergonic example, you see the exact opposite. In this case, you can see that the transition state is closer in energy to the products than to the reactants. And that means that the transition state will more closely resemble structurally the products than the reactants. In either case, the stability of the transition state will be affected by the same factors that influence the stability of what it resembles. So if we look back at the free energy diagram for our hydrohalogenation, we can see that in each case, the first step is the formation of a carbocation. And the formation of the carbocation is endergonic. And that means that the transition state will more closely resemble the product of that step, that is, the intermediate, the carbocation, than it will the reactant. In other words, these two transition states look an awful lot like carbocations. And a transition state that looks an awful lot like a tertiary carbocation is going to be more stable than a transition state that looks like a primary carbocation. And that's why we can state that the transition state along the green path is lower in energy than the transition state following the red path. And that means the green path will be a faster reaction. So we've got two more types of electrophilic addition reactions to look at. The next one is the acid-catalyzed hydration. Hydration literally means just adding water. And if you look at this example, you can see the alkene added water across that pi bond. And you can see that the OH went to the more substituted carbon of the alkene, and the H went to the less substituted carbon. And that means that this acid-catalyzed hydration follows Markovnikov's rule, where HX, in this case the X would be hydroxide, the X ended up bonded to the more substituted carbon. You can see that the reaction produces an alcohol. Now, if we look at the mechanism, you'll see that it closely resembles the reaction mechanism for the hydrohalogenation. The first step in hydrohalogenation was the protonation of the alkene by the strong acid, HBr or HCl, whatever. Those acids were sufficiently strong enough to protonate the alkene, which is actually a very weak base. Now, if you pour water on an alkene, all you're going to get is a wet alkene. And that's because water is nowhere near acidic enough to protonate an alkene, which is a very weak base. The way we get around this problem is by adding a catalyst, specifically an acid catalyst. In the presence of a strong acid, water will react to form hydronium, which is in and of itself a strong acid. And hydronium is a strong enough acid to protonate an alkene. And so the first step here is essentially identical to the first step in the hydrohalogenation, except now we're using hydronium as the acid. So in the first step, the pi electrons push towards the electron-deficient hydrogen of hydronium to make a CH bond. And of course, hydrogen can only have one bond, so the existing HO bond must break. And that pushes a new lone pair onto the oxygen, creating water. And that means we're going to form a carbocation. Well, possibly two, but from here on out, we're only going to draw the more stable major carbocation product. And this is why this reaction follows Markovnikov's rule. The formation of the more stable tertiary carbocation will occur more quickly than the formation of the primary carbocation. So in the second step of the hydrohalogenation, the resulting halide, like bromide, simply attacked the empty orbital of that carbocation, and that formed the final product. In this case, because the acid we have is hydronium, well, the conjugate base of hydronium is water, and so now water is our nucleophile in the second step. Regardless, it's the same thing. Water will now attack that empty orbital on that carbocation to form an oxygen-carbon bond. But as you can see, that doesn't make our final alcohol product. It actually makes the conjugate acid of the alcohol product. And that means it simply needs to be deprotonated. This intermediate is actually called an alkoxonium ion. It's just, again, the conjugate acid of an alcohol. So there's a third step here, and that third step is simply the removal of one of those hydrogens on the oxygen. In this case, it's likely that another water molecule will come around and act as the base. So here we have the electron-rich oxygen of water attracted to the electron-deficient hydrogen of that alkoxonium ion, so those electrons push forwards towards that H, creating a new OH bond, and again, H can only have one pair of electrons on it, so we have to push electrons off at the same time, so the HO bond breaks, depositing a new lone pair onto that oxygen, and that makes the final alcohol product. And if you look closely, the first step involved the reaction of a hydronium ion, and the last step formed a hydronium ion. And that means that overall, acid was not consumed in the reaction. Only the alkene and a water molecule were consumed. And that's why the reaction is catalytic in acid. The acid catalyst enabled the reaction to occur, but was not consumed by the reaction. The last electrophilic addition we're going to look at is halogenation. And it's simply the addition of a dihalide like F2 or Cl2 or Br2 across a carbon-carbon pi bond. So here I show that same alkene now reacting with Br2. And as you can see, regioselectivity is not a concern here. In a halogenation, you're adding the same piece twice, in this case Br and Br. The mechanism for halogenation is a little bit different than what we've seen for hydrohalogenation and the acid-catalyzed hydration. Again, the alkene will serve as the nucleophile, and now the dihalide, in this case Br2, will act as the electrophile. In hydrohalogenation, the first step was to protonate the alkene, and in this case, that's not what's going to happen. The nucleophilic alkene is actually attacking a halogen, a bromine atom in this case. As the pi bond breaks, a new carbon-bromine bond forms, and that's going to exceed the octet on the bromine, so once again we have to push electrons off, this time again forming a halide anion. As the pi bond breaks, one of the carbons starts to become electron deficient, because the atom that is being attacked has a lone pair on it. that lone pair can now donate back in to the developing positive charge. So we have a third curved red arrow here. The bromine atom that was attacked by the pi electrons will actually be attached to both carbons of the alkene now. One bond formed from the pi electrons attacking the bromine, and the other bond formed from a lone pair on that bromine attacking the other carbon, neutralizing the developing positive charge. Because that bromine atom is now attached to both carbons, it forms a three-membered ring, called a halonium ion, in this case a bromonium ion since it's made with bromine. The bromonium ion is electrophilic, and of course the bromide that formed is nucleophilic. Be aware that it's the two carbon atoms of the bromonium ring that are electrophilic, not the bromine. Don't let that positive charge throw you off. Remember, the carbon-bromine bond is polarized so that the carbon is actually electron deficient. So the bromide will be attracted to one of the carbons of the bromonium ion, pushing one of its lone pairs in to make a new carbon-bromine bond. That's going to exceed the octet on the carbon it attacks. And that means electrons must be pushed off of that carbon at the same time. Now, that carbon has four bonds that could potentially break. Two CH bonds, the carbon-carbon bond, and the CBr bond. And if we think in terms of energy, it'll be really obvious which bond has to break. We know that CH bonds are very strong because of all the S character associated with the hydrogen atom. Carbon-carbon bonds are a little bit weaker, and the CBr bond is actually very weak because it involves that very large bromine atom. So the CBr bond is the weakest bond, it's the most likely to break. Breaking the CBr bond will also open up that strain three-membered ring, relieving ring strain. And lastly, breaking that bond will allow the bonding electrons to be deposited onto that electronegative bromine. Bromine's electronegative, it wants that electron density. So the bromide attacks that carbon, making a new CBr bond, which actually breaks one of the existing CBr bonds in the bromonium ion. Just make sure that when you draw out this mechanism, you do not have it going through a carbocation. It's a really common mistake. This reaction does not go through a carbocation, it goes through a halonium ion.